So, Assalamualaikum and good morning. Selamat pagi semuanya. Harap sihat-sihat semuanya. Jadi ini kiranya hari terakhir ya, Zahida. Yep. Our last day of the Indonesian Mathematical Society, right? IndoMS, which is actually our second class and our last class. Okay. Are we expecting some more students or some of them are not joining?
Usually they will
come later.
Come later. So you can start now.
Okay. All right. If you remember last class, we went through some of the basics of groups. Okay. If you still remember, you tell me what are the name of the groups. So, Nidia, since you're the moderator and the class monitor, everything.
Okay, so the groups are the dihedral group.
Yeah.
Dihedral group, and then generalized quaternion. It's the Q for N, yes. And then quasi-dihedral. Quasi-dihedral is QD to the power of N. Yes.
All right. And we also have 3 graphs, right?
Yep.
Which are?
Non-commuting graph. Non-commuting graph, yes, and C. And then there's the conjugacy class, CC.
Conjugacy class graph.
Then the last is coprime, CO, yes.
Okay. Refreshing the memory.
Okay.
Okay, Bu Zaida, Dr. Idayu is here. Ayu, if you can just turn on your camera, if that is possible. Okay, that is my ex-PhD student. She has been helping me with all the notes and everything for this class. And later in the afternoon, she'll be also helping me with the tutorial class. You will be bored with me after 3-4 hours, right? Okay, so it's glad to see you here, Ayu. Thanks. Maybe next time. Last time we went to Jakarta, right? You remember when Professor Dia from Taruna Magara, I think the name of the university, invited. So we went there and presented some of the related research there. There's a conference also. Okay, now groups, graphs, and we have 3 or how many topological indices? The last time we already have 1, right? Remember the winner index. Okay. Now you have to know, I actually went through Dr. Intan's, Bu Intan's, okay, class. Just want to see what she has been teaching you, all right? And I can see that she has covered a lot also about the dihedral group and the non-commuting graph, right? Some of those, and some of the coprime graph a little bit. And I went through also my classes, my lectures, just want to see what you have been seeing from Zoom to see, making sure. That's why I put this dot. There's a light coming in from there. That's why probably you cannot really see this part. But there is one place that I put this. What I meant is actually S6, P6, sorry. So there was a mistake there that I didn't realize. This is the right one. So if you went back and look at your notes, make sure you get this right. Okay. Okay, for this one. And when I introduce the non-commuting graph, first I write like this. So when you go back, you will put a slash, non-commuting. After that, I mentioned about this, but I realized before I didn't put the slash. Okay, now non-commuting graph, the vertices would be G without the center, right? And two vertices are adjacent if we have this. Okay, conjugacy class graph, the vertices would be all the non-trivial conjugacy classes. This is the vertices. And they are adjacent if this one is 1. Right? So this is for the conjugacy class graph. I just mentioned this because we will be using it again today. And the co-prime graph is the graph. What is the vertices of the co-prime graph? You remember? Nidia? What's the vertices? Don't remember. I will mention it when we went to that. Anyway, today we will go to the second winner index. All right. Okay. Okay, we have 3 classes this morning, right? The first one, we will talk about the Zagreb index, okay? In the second part, we will talk about the, okay, so we have first already this. The second index will be the Zagreb. And this one, the third one will be the Zagreb. And the last one will be the Harari index, okay? Okay, so this already done in the last class. If you remember, we counting the distance, right? The double sum of the distance for each of the vertices, that is the winner index. Now, for the Zagreb index, we have first Zagreb index, and we also have second Zagreb index. All right. So still, our graph has to be connected. Look at the definition. Okay, let this be connected. And the vertex, I already uploaded actually last night the notes. You see it, Nidia? Yeah? All right. Okay, so the vertices of this is 1 until n. Okay, now the first Zagreb index, we call it M1 of the graph. Okay, this is the sum of the degree of each vertex square. The sum of the square of the degree of each vertex. So V is for all V. Okay. Last time we look at the distance, right? This one we look at the degree. And how do you define the degree? Last time we already defined the degree is how many edges connected to that particular vertex, right? And the second Zagreb index. Okay. Ibu Zahida sudah share di chat ya. Okay, M2. Okay, this is the sum of the product of the degree. The sum of the product of the degree of two vertices for each edge. Yeah, degree of U, degree of V, and UV is in the set of the edges. CC, right? Edges. Yeah. Okay. For each of the edge, we have the two vertices. So you have to multiply. Then take the sum. Okay, it's senang ya. Senang, mudah.
Yeah, mudah.
Mudah. Okay.
Senang here, happy.
Oh, senang, happy. Okay, mudah. Easy.
Yes, easy, mudah.
Okay. So next will be the example, right? We will calculate this. Okay, so example. One, two, three, four. The first edge, the second edge, the third edge, the fourth edge, and the fifth edge. So this is just a simple connected graph. So compute the first and second Zagreb index of this. Everyone has breakfast already? Nidia, what do you have for breakfast?
I have porridge, chicken porridge. Yes.
That's nice. When I went to Indonesia last time, even the breakfast is quite heavy. You know, I remember when I went to Dr. Idayu last time, she really enjoyed the food in Indonesia. Right, Dayu? Looking for all the sambal hijau, sambal merah, really the pedas-pedas one, I cannot stand. So whatever sambal, I will pass to Dr. Idayu.
Actually, I'm grabbing nasi kandar.
Nasi kandar in Penang.
Yes.
This morning I had lontong. Lontong is actually soft. I'm not sure if you have it over there.
Yes.
Yes, we have it.
Ah, I also like gado-gado. That is my favorite.
Oh.
I'm talking because I'm waiting for you to find the solution.
It's currently computing right now. Wait.
Yeah.
Ayo kerjakan itu.
Ini cerita pasal makanan ya. Okay, so M1 of the gamma, writing out the formula. Okay. Now if I use I as the degree of the vertex, yeah, just to see the index. 1, 2, 3, 4, right? So we have the degree of the first one. What's the degree? 3, right? 3.
Squared. Yeah.
Second one,
2. 2 squared.
the third one,
3 squared.
and the fourth one.
2 squared.
So mudah ya.
Iya. 26. Yes. Oh, 26.
Okay. Now we go to the second one. Little bit longer than the first one. Boleh padam ya?
Yes.
Padam.
Okay, so it's the sum of the degree U, degree V, in which UV is in the edges. Okay, so we have to choose, like for every single E. So for example, with this E, right?
Mm.
E, E1, you have to choose degree 1 and degree 2. That will be 3 times.
Times 2.
And E2, 2 times 3.
2. Which one?
E3,
3 times
3 times 2. E3
Yeah.
is 2 times
2 times 3.
E4,
3 times 2.
E5,
3 times 3.
3 times 3. The answer is
24, 33.
30. Okay, mudah.
Yes.
So
Mudah.
try to visualize what if it's a complete graph, right?
Oh.
The complete graph, you know how many vertices, how many edges in each of the edges, you know the degree, right? So you
Yes.
start thinking about, say, it's 4 kn, the degree of the vertices, we know it's
N minus 1.
right? And then you have how many vertices, that will be n vertices. So while we are looking at new definitions, coming up with an example, you always have to think of what kind of properties that you can think that you can have from this any new definition. So this is what we call research, yeah, Bu Zahida. And then we try to find problem. Our problem, mathematics researcher, is to find problem.
Yes.
If there is no problem, it is a problem to us. So that is what we do. We find problem. All right. So I have covered this, and then we are interested to see and to find the indices for all those graphs associated to the groups that we have, right? Okay. All right, so let me write this lemma. This lemma actually will be used in the theorem that I'll just state this, then you can see what kind of preliminary result that you need for our proof later. So I call this lemma 1. So this is regarding the first group, which is
Dihedral.
So let G be the dihedral group. And we start with D6, yeah? And also I have mentioned about this, and also Dr. Intan also mentioned about the centralizer, right? Okay. And the centralizer and the order, the sum of the order sum of the square of the order of the centralizer, when we take out the center, again we have to separate into two. One is when the case n odd, and another one when the case n even. Okay. And this is equal to n cubed minus n squared plus 4n, n cubed minus n squared. How do you say this in Indonesia?
N quadrat.
N
Quadrat.
Okay.
Yes.
When I listened to Dr. Intan's lecture, so I tried to learn a little bit of quadrat, yeah. Okay. So now you can see why there is something like the sum, something with the square, right? It's very close to the definition of the index before. So this is quite interesting result in which, given the n, n-gon, n-cis here, for the dihedral, you can use that value of n to get this summation. So this depends on n, when n odd n, n even.
And even.
Yeah. I'm not going to go into the proof, but I have already given the proof in the notes, right? You can go through. So in the case in the future, if you do something or research related to this and you want to get this kind of result, and how do we get to get this result, then you can see at the proof. This related to also about the centralizer of the elements in the dihedral group. Which one commute and which one do not commute with the rotation and reflection. Yeah. Okay. Lemma 2, again we have let G be D to N. Okay. And the same thing, yeah. CGX is the centralizer. Now, the second Zagreb, we have the product, right? So you have the product of these two centralizer whenever we have xy in the edges of the graph. Okay. So this is equal to 2n, n squared minus 1. Again, we have to separate into two cases. And for n squared minus. Okay, so later on, we trying actually to generalize, okay, the result for this Zagreb index. Okay, and the proof goes to finding the relation in between the centralizer and the edges. You can go through step by step, pretty clear for this one. So let's look at the first result of Zagreb index for those graphs related to dihedral groups. So the Zagreb index of, I just put here, non-commuting graph. All right. So the first, I call it proposition 9. Okay. So I just write this out. The first Zagreb index of the non-commuting graph for any finite group G the first Zagreb index of the non-commuting graph of any finite group G is equal to, for any graph G finite, we can find the order, okay? Finite is, how do you say finite in Indonesia?
Berhingga.
Terhingga, okay.
Berhingga.
Terhingga. Okay, not finite, yeah? Not finite.
Infinite, yeah.
Because infinite. Okay, so the order of G squared times the order of G plus the order of the center, okay, minus 2 times the number of conjugacy classes. Okay, so the order of G squared times the order of G plus the center minus 2 times the number of conjugacy classes minus the order of the centralizer square. And you see, this we got before, right? You can plug in later to get the answer. Okay, and for the second Zagreb index, okay, I didn't say about any group. I just mentioned about the finite group. Then you see, you can put in any finite group later. Okay, so the second Zagreb index of non-commuting graph of G is given as negative the order of G squared, the order of E edges of the non-commuting graph plus the order of G multiplied by the first Zagreb index of this. Okay, multiply by the first Zagreb index plus the lemma that we found before, CGX, CGY. Okay, XY in E. So again, if we want to find this, that is why, since we can figure this out from the group, we can find the number of edges from the graph, we can find the order of the group again. We already counted the first Zagreb index. So this is the part that we need from the previous one for particular group that we want to find. Okay, so you can see where we are going and how we can get the first Zagreb index of the non-commuting graph for D to N. All right. You don't actually have to copy this because it's there, but sometimes when I was a student, I want to see my own writing, so I will write. Betul ya?
Yeah, but we write it after the class over.
That's true. Because reading math is really different from doing math. You cannot read math. You have to do math. So that okay, boleh faham, okay boleh ngerti ni semua.
And for me, I cannot write and listen the explanation.
Yeah, that's why we just look and listen and understand. Then after that, because you already have the notes. But sometimes during class, if we don't have any notes, how do you actually want to understand at the same time by copying and writing, right?
Yeah.
But now we have Zoom, we can screenshot, so that's a good
After
thing. I
that,
don't want to say
you write
pandemic
the
is good, but something good out of the physical class. Okay, so our first theorem. So this is of the theorem. Okay. How many of you here are undergraduate? S apa? S1 ya?
Satu.
S1. Undergraduate.
Coba raise hand. Yang S1.
Oh, this morning I forgot to ask everyone to turn on the video to see the face, right? The morning face. S1 angkat tangannya, jarinya. Okey, ni dia S1. S2. S2 tak ada satu. Ada few ya. S3.
S3 looks like they ask permission.
S3 is PhD,
Doctoral.
right?
Yes.
S3. Okay.
Yeah.
So most of you are S1. Okay, S1, S1, and then master, you probably are interested to do PhD. Yeah. Bu Zahida boleh ambil jadi penyelia. Dr. Idayu here, she was my student in S1 for the final year project. And then in UTM, there is a special program which is called fast track. So if you get a first class student in S1, you can go to S3. So Dr. Idayu went from S1 ke S3, and then she finished recently her PhD, submitted in 3 years. So later on you ask Dr. Idayu for the secret. You can ask her email from Bu Zahida.
Okay.
Okay. Oh, right. Theorem, yeah. So M1, the first Zagreb index of the non-commuting graph of dihedral group. Okay. So this is n 5n minus 4 n minus 1. So we have to have again two cases here, n odd and n even. And 5n minus 8 n minus 2. You will see later when we have the conjugacy class graph in which we have to break this into another two cases. Do you remember? The one when it's even, n over 2 is even and n over 2 is odd, right? So there are more cases for that one. So you see, you given me a dn, d2n, so using just that order n, you can figure out the first Zagreb index, okay? And the proof is quite straightforward. It uses the previous proposition and plugging in from the lemma, okay? You can, after this, you use that proposition that I share, and also from last class, I share about what is the order, right? What is the center, plug in those proposition, and the one that I shared today, and also the lemma, all the numbers, including n and the factor, right? Then you can figure out this. It's quite straightforward. So sometimes you want to prove something big, you break up into smaller case, and then you just plug in. Okay. So I think that is straightforward. Zahida, I'm sure they can follow through and do that proof. Okay. The second one, when we have time, sometime today, I will try to see to show the proof for at least one. Yeah? Okay, I just want to show you the steps, because by having all those formula before, and I'm sure all of you can just plug in the one that we have before. You see there is the center, there is the order. So based on the proposition and lemma, you follow and then you plug in, then you get the solution. Okay, now this one is M2, non-commuting graph of D2, right? The second Zagreb index. Also, we have into two cases. And this is with all the square, right? when I began the class, I mentioned about the boiling point in which the indices are used by the chemists. And in many cases, the chemists actually use some results from whatever mathematicians have found in some of the places. In some others, they really need to do in the laboratory. So in some cases, you can actually compute it faster and do it theoretically. But there is another research of mine which has something to do with biology. So we do the computation in, it's a little bit about DNA computation and splicing system, in which we really want to see how this is done in the lab. It took so much time to get the result that we can actually already predict theoretically. So this is quite interesting. Okay, so this is the result for dihedral. Right, now I want to share about the Zagreb index of conjugacy class graph for dihedral group. Correct. So we call it theorem 3. I can erase just that, you cannot. You have to rewrite, right? So that's why I like this whiteboard. Conjugacy class graph of G. Okay, this one, or we use the result from the winner index. Okay, it turned out that this is n times the winner index of this. Okay, all right. Okay, so let me try and prove this one. If you remember the winner index of the conjugacy class graph for the dihedral group of 2n, that was from last time. All right, it's K, right? The winner index is K. That's something in the bracket, right? Kg minus center, right? Yeah. IU is here. If I make a mistake, you can easily let me know. Okay, so this is from the first class. Okay, so we want to, okay, what is n? N in this case is 4k, yeah? N is 4k, right? N is 4k. Okay, so this is what we want, right? Let me see how we are going to prove this. Okay, so based on proposition 2, you have to recheck this proposition. The number of conjugacy classes is, so we have the case when n is even, and n is even, the number of conjugacy classes is n plus 6 over 2. Okay, and from theorem 2, we have two cases, yeah, for n even and n odd. So for the n even, the winner index of the conjugacy classes of D2n is equal to n over 3. Okay. Now, from proposition 2, also the total number of vertices, for the conjugacy class graph for D2n is equal to n plus 2 over 2 when n is 4k. So with all this information, you want to find now the first Zagreb index of this using the formula in which this is the degree, right? Degree of, we call it I squared. Okay. I from 1 until all the number here n over 2 n plus 2 over 2. And n is even, yeah? When n is even, this one is even, this one is n integer, right? You can divide by 2. Okay, so this is the degree squared of 1 squared, degree of 2 squared until degree of n plus 2 over 2 squared. Now, for this particular one, you have n plus 2 over 2 of each of these is this. N over n plus 2 over 2 minus 1 squared. Okay, because each of those has this degree, n plus 2 over 2 minus 1, right? Okay, so so this is given to be k of g minus the center. You can rewrite this. Okay, this is minus 2, so you have n over 2 squared. So this, which is 4k squared kg minus, okay, which is equal to this. So you see that for this particular conjugacy class graph, the first Zagreb index is related to the winner index. All right. Then, okay, this is already in the notes. Okay, you can look again. But this is how you do it step by step using the definition, right? When we do this, of course, for research, you have to do this first, and then you figure out where is the whole, right? The whole is looking at the detail and get the result or the formula for the little one. Take that out and bring it in front, call it like lemma or proposition. Then you plug in, right? Then I want to give you the next theorem. Is the second Zagreb index of D to N, which is also related as before to the first one, right? N over 4, M1. And for this one, we restrict, like before, that this is the case when n is 4k, yeah? Theorem 3, if I missed to write it out, I just mentioned that the n that we do is when n is 4k, a multiple of integer, not for the odd one, for the D to N. And the same thing for this one. This is the one that we can generalize. Okay. How do we prove this? Is by using the definition, okay? The sum of the degree of the edges, right? All right, let me move on to the first Zagreb index. of co-prime graph. Oh, I can just do this. Co-prime, that's like cheating. For D2N. So the first case is when N is odd. N is odd. Yeah. So I call this 5 and 6. The first Zagreb index of this is equal to N 2N squared plus 5N minus 5. Okay, so G is the Zagreb group, and for N odd prime, the first Zagreb index is this, a polynomial of degree 3. Okay, and go back to looking at the co-prime graph of D2N when N is odd prime is multipartite. Now I know Indonesian language. The multipartite graph, multipartite K1 N minus 1 N. Okay, you can go back and look at this. So we have vertices of certain degree in the multipartite graph, right? With degree to N minus 1, with degree N minus 1, N plus 1, and degree N. So just plug in the degree in the summation. Okay, that is pretty straightforward. You have the sum of the degree squared for all those I from 1 to N. So plug in the degree from the multipartite into the formula. You will get this directly right away. Then for this one, okay, so for this one, this is only for, it depends on our graph. When we have to go back to see the graph from the previous lecture from before, it depends on the N. Some of the graph, we can only find the general one for certain N. So for this one, N is 2 to the K. For this particular one, we can generalize this. So I still go to the first one, yeah? So I want to go to the first one first. Okay. Let me change here. So just now it's odd, now it's 2 to the K. So for this one, this is 2N minus 1. Okay, in some of the cases in which we have dihedral with just any even number, because 2 to the N does not cover all even, right? Like 6, it does not cover, that one cannot be generalized. So we have to restrict this depending on the graph that is also connected, right? If the graph is not connected, because we have to have the connected graph in the first place. So you have to go back to the definition and see for that one. Oh, I have only 1 minute. Yeah, Nidia?
If you want to continue, it's okay.
It's okay.
Okay, I'll just finish a little bit because only first and second Zagreb index of co-prime. And we can take a 5-minute break. You need to go to, what do you call the restroom?
Toilet.
Toilet. In Indonesia, you call it?
Kamar mandi.
Itu untuk mandi.
Toilet.
Toilet juga ya. Okay. Let me go for this one first, yeah. Okay, this is 4N is 2 to the K, right? And this is direct from the definition, okay, to find the first Zagreb index. Okay, now let me go to the second Zagreb index for the first case. N odd. Okay, so M2, D2, C0. Okay, this is N to the 4 plus 4N cubed minus 3N squared minus 2N plus 1 is polynomial with that degree 4. And for this proof, because we are looking at all kind of edges, so you have to look at the edges of the graph, and then you find the degree for each of the edge, the degree of the vertices, and then you multiply and then you sum up. Yeah. So these are all involving the n. When n is 2 to the k, okay, so for this one, it's equal to 2n minus 1 squared. This is the second Zagreb index of the co-prime graph of D2n. All right, so that's the one that I want to show for the Zagreb index. And you remember we still have the other groups. Yeah, we still have the other groups. So I have covered for dihedral for the first and second Zagreb index for the 3 graph for dihedral. All right. Then you also have results for the Zagreb index, first and second Zagreb index for the second graph, for the third graph, co-prime we did. Okay, for all graph, for generalized quaternion group and quasi-digit group. All right, that is a whole set of results. I'm not going to go into one by one because the routine is very, very similar. But you can see the results are given as in the notes because I want to cover at least different indices, right? So you can see the pattern now. You can follow through and you can do it for the different graph for the different groups. So I will stop here and we'll come back 10 o'clock your time.